Alright, in this lecture we're going to extend the ideas of work being done by gases, or two gases, which we started in the last lecture. And here's kind of this classical setup where we have some weights on a piston. This we'll consider the piston, and some gas inside. And the gas, each particle kind of moves a little bit differently, but overall it's going to have a certain temperature to it. And unlike in the previous case, what we're going to look at here is the situation where we don't have that much weight on top. So there's sort of this downward force of gravity, but the upward force of the gas, due to the gas's pressure, is going to be larger. So we'll call this force of the gas. And this force of the gas being larger upwards causes a displacement. Now, unlike in the previous case, where we were basically adding heat, in this case we're not going to add heat. So we're just going to extend this upwards. It's going to move up, move up, move up, but the rate at which it moves up will slow down, and eventually it'll come to a point where it stops moving up. The reason for that is because these forces start to even out, not because this one gets larger, but because this one gets smaller. And the question is why? Why would the gas be exerting less force if it moves up a certain distance, which I'll highlight here. So it moves up this certain distance. We've displaced it by a certain volume. There's a couple different ways that we can look at it. One thing that we can do is we can imagine that there is, let's say, a wall. Maybe it's a truck. Okay, so let's say we have a truck, and this truck is moving away from you. And you take a super ball and you throw the super ball at the truck. So the super ball is moving with a certain speed. Well, if the truck is stationary, the super ball is perfectly elastic, so we'll assume that it's the perfect super ball, then the speed with which it hits the truck is going to be the same as the speed with which it bounces off the truck. But let's consider the case where the truck is moving. I'll see what I can do here, trying to get fancy with my features. So you have this truck, and we'll do 3 different cases with it. I'll do this one up here. So in the first case, you're taking a super ball and you're throwing it at it, and it bounces off with the same speed. In the next case, the truck is moving away from you. So it already has, and it's a little too big of a velocity, so it has this velocity forwards. Well, what's going to happen is the ball's going to come in, same speed as before, but when it bounces off, and you can imagine this, it's going to bounce off with a velocity that is this one, basically minus that. So it's only going to bounce off with a little bit of velocity this time. It's essentially transferring the energy to the truck to get it to move forward faster. But the other way to think about it is just from common sense. You throw it at it. It's sort of like there's somebody catching it and throwing it back. If the truck's moving away, it's not going to bounce off nearly as quickly. The other case is, what if the truck is backing up towards you? So the truck has this velocity backwards. The ball comes in, same speed as before, but it's going to bounce off with a combination of this speed plus that speed to come off even faster. The truck is imparting energy to the ball. So this is one way to think of it, and the surface of the piston kind of behaves the same way. If it's going away, the ricochet is not going to be as energetic as if it's going towards it. Another way to think about it is kind of like when we talked about the tissue, like hitting the tissue, or the problem with driving a car on sand, is that when you apply a force to something and it moves away from you, which is what's happening in the case of the truck, or what's happening in the case of the piston right here, is you're not able to apply as large of a force. And so what's going on is we need a force to cause a large acceleration for the super ball. Since the truck's moving away, or it moves away when we throw the super ball at it, we're not able to get as large of a force, and as a result, the velocity change isn't as great. In this case, since it's moving towards us, we're able to get a large force being applied, and the result is a much larger velocity out. And the final way to think about it is just from an energy standpoint, which is that you have this object that's applying force. You have to apply a force back. So if you're successfully moving it away, you're successfully doing work to it, positive work to it. Well, where does the energy come to do positive work? It comes from the energy of the particles. So they lose energy, they start to slow down. The other case would be if this is actually dropping. If this piston is moving down and compressing the gas, then we would be taking energy from the piston. In this case, gravitational potential energy. We'd be using the gravitational potential energy of these weights to do work on the gas, to speed up the gas, to make the particles move faster and faster. But in this case, we'll just focus on this case where we have this gas. It's applying a larger force than the force of gravity against it. And the result is that we do work. The particles slow down. So we have these particles, they're going to slow down. And with less speed of the particles, that means a lower temperature. So what's going to happen here is we're going to cause a decrease in the temperature. So these particles will cool down as this expands. This is different from what we did in the previous case where we kept the temperature, or we were adding heat to it. So we were preventing the particles from cooling down. And what we're going to do next is just take a quick look at an equation that hopefully you remember from chemistry. So here's your ideal gas law, which you learned in chemistry. It's important to remember that it is ideal, so it doesn't really reflect reality, but it's a decent approximation. And what it says is that we have the pressure times the volume. This is the pressure of the fluid. In this case, we'll be talking primarily about gases. And we learned all about that. The volume that the fluid's taking up. And that's equal to N times R times T. Well, N is just basically the amount of the stuff. N is a constant that we use to convert units. And T is related to the average kinetic energy of the particles. So we have the mass that's involved, and we have the amount of stuff that's involved, and we have how much the stuff is really moving as our primary things on the side. And that's proportional to the pressure that's involved and the volume that's involved. Well, let's try to delve into this a little bit more to understand what's really taking place. And that's what we're going to do in just a moment. So we go back here and we have this equation, P times V equals nRT. And primarily we're going to be focusing on P times V is proportional to the temperature. The reason why we're going to do that is because we're going to assume that we haven't changed the number of particles that are inside of this container. And this universal constant probably not likely to change either. But if this is what we're dealing with, this equation right here, we have a pretty boring situation. Because it's saying you have a pressure, you have a volume, there's going to be a certain temperature associated with that. What we're doing in this case is we're actually changing the volume. So we have this, pressure times the change in the volume is proportional to the change in the temperature. And this right here, this P delta V, this is work, right? We had a force per area times distance. That's what volume is. It's the surface area, the cross-sectional area, times the distance it moved. And so we wind up with work. So work is proportional to the change in the temperature, which should make perfect sense because temperature is related to the average kinetic energy, and we had that work energy theorem, which basically said work is equal to the change in kinetic energy. So this should make perfect sense. Work is proportional to the change in temperature. How do you do work? By having a certain pressure and by changing the volume.